about the race we have between who is better in solving fermion problems called atom experiments or the quantum Monte Carlo simulations, because we've been told that actually you can build an optical lattice emulator that will solve all the problems of condensed matter physics and more. They can just build your model in the lab. It costs about $1 million or $2 million. And the basic idea is they take a quantum gas, a cold one, in a trap somewhere. They cool it, and then they let it fall. That's the ball up here that they let fall. As it drops down, the fast atoms fly farther. And if they later take a picture, that picture reflects the more momentum distribution of the atoms. So when one then does that for boson and cools it down, they see this peak appear in the center. That's the Bose condensate. Now that's trivial. What about fermions, and what about fermions in the lattice? If one adds some standing waves of lasers, one gets the optical lattice. One loads the fermionic atoms now into that lattice, and if the lattice is deep, it is described by a Hubbard model. There will be a hopping term T. There will be a cost for having two atoms on the same side. And that way they can build the Hubbard model and measure anything we want to ever know about the Hubbard model. Does it work? At first one has to check whether it works for bosons where we solve things. So we had a project where we did something that was different than usual, because usually we want that the model reproduces the measurements. Here we calculated things for trap bosons, about a million bosons in the right trap and lattice. And this time the task was that the experiment should reproduce what we calculate, and that worked. These curves here is the quantum Monte Carlo. This is the momentum distribution for the bosons in the lattice. They agree, but the quantum Monte Carlo is the cleaner, less noisy. So for bosons we've won, but that's what they always thought. Boson is easy, but what about fermions? Because fermions is the problem, as we all know, and we have no black box solution for the fermions unless they have one for us. But the design problem doesn't mean that we cannot simulate fermionic models. We just have to find the right approximation that is good enough. And for the cold atoms, while we can't reach the ground state in quantum Monte Carlo, they can't reach the ground state so far either. And they work in a temperature regime that's about the same temperature as the hopping. And in that regime, the sign problem isn't too bad. In that regime, nearly the high temperature series works still at first, and then going to low temperature, just we have quantum Monte Carlo methods that work well, but we can still do what they can do down to even 3 times lower temperatures. So far we still win with the CT-QMC, and I want to show you how we do that. Namely using a continuous time quantum Monte Carlo methods. So what is the basic idea behind those methods? The basic idea is we start from a diagrammatic expansion. Let's look first at the lattice model or the continuum model. We have first order diagram in a Hubbard model, second order diagrams, then there are many third and fourth and so on. We can't draw all, but we can sample them. The weight comes, there comes minus u from the interaction vertex, and we get the Green's functions as the weight for the propagators. That gives a bad sign problem. Once we sum up the topologies into determinants, the sign problem vanishes if u is negative and if the population species are balanced. So that is the same matrix for the up and down fermions. For the repulsive u, yeah, it works at half filling in a lattice by doing particle hole transformation on one species. Now, one basic question that I've been asked often is, how can one work in continuous time? If we have, so how can we take the Trotter time step to 0 and still have something that works? And I want to ask if you know how that's done, or if I should explain that in detail. Explain it, yes. I'll show what the problem is with the naive way, because I've been told for many years that one cannot take the Trotter time step to 0. And the reason is just because then all the acceptance rates vanish. Let's look at a simplified model where the partition function is sum over the orders k, and I just have a weight that depends on the order k. And I want to sample from that partition function. The way I do that is pretty easy. I have one type of move to insert and another order at some time, or have the move to remove some vertex at some time tau. And they have to be balanced. And the weight of the configuration is simply w of k d tau 1 up to d tau k. That's infinitesimally small, but we sample from it. Now, what if you want to insert another vertex? I can now say, let us write down the equation for I want to insert the next one at a new time tau k plus 1. And I need to write down the detailed balance equation for the insertion and the removal process. And now it depends on how you think about that. One way to think about that is how we would do it in discrete time. And there we would just split it into discrete time steps. And we would pick one of those times. There might be m tau time steps. So I have 1 over m, the probability of picking that location. And then I choose whether I want to insert it or not. And this here scales like delta tau. So when I look at the ratios of the weights. The weight before was this. The weight afterwards is W of k plus 1 times d tau 1 up to d tau k, and there's a new d tau k plus 1. If I look at the ratio, then those here all cancel, and then I'm left with the ratio of the weights of the weight of the new one divided by the old one. That is W of k plus 1 times d tau k plus 1 over W of k. So if I say the insertion is I pick a time and the insert, the removal is I pick a certain time and I remove, then the acceptance rate vanishes as I let the time step delta tau go to 0. And that's why people told me you should never think of taking the limit exactly at first, until Russians told me, no, it's totally easy. You just have to rethink what you do. And the idea is we don't pick a certain time step for the insertion, and then for the removal we don't go there and say let us pick a certain time, because it makes no sense, because there will only be a finite number of negative vertices, and you will just never hit the right time. So the idea is for the insertion we pick a time, tau k plus 1, and for the removal we pick a vertex j that we want to remove. And that way things become balanced, because now what is the probability of picking a certain time tau k plus 1? The proposal probability, let me call it P propose, for the insertion is d tau k plus 1 over beta. It's infinitesimally small to pick to one time. And the proposal for the removal is P propose for the removing. That is just for I pick one of the k plus 1 vertices for so that is 1 over k plus 1 for the removal. And now I need to write down the acceptance here probability for the metropolis rule. This will be the ratio of the weights. So I have the W of k plus 1 over W of k. I have a d tau k plus 1. And I have to also take into account the proposal ratios. That is for the removal will be 1 over k plus 1. For the insertion it is d tau k plus 1 divided by beta. And now that final d tau cancels, and we get that the acceptance ratio here just becomes the ratio of the weights wk plus 1 divided by w of k times beta over k plus 1. And it's finite. So what one has to do just is let's say I insert at the randomly chosen time and I remove a randomly chosen vertex, and those two balance with the finite acceptance ratio, and there's no problem with the continuous time. Writing down the detailed balance equations becomes tricky sometimes. I've had students spend a month or two on making things really work in the end, but it works. So there is no problem with that. And so here we would just insert a vertex somewhere, remove it somewhere, and things just work. Why do we want to go to continuous time if it's so much harder to derive the detailed balance equations? The problem there is not the equation, the problem is really knowing what your code has done, how you picked a certain side and the time and so on. One reason is that if we go to continuous time, we don't suffer from Trotter error. We don't have to extrapolate in the Trotter time step. Just a single calculation is enough. It is conceptually easier because we just do a perturbation expansion, and we also need less time and less memory. Because if I have some path integral somewhere, then I want to discretize it on a time scale that is much, much finer than the typical features in the path integral. So in the Hubbard model, I would need to choose a time step delta tau that is much smaller than the hopping matrix element T. While for the continuous time method, I just get the hopping or the interaction events, and I don't have to be so fine. And then also the memory will be less and the CPU time. Now, the problem though is there's still the sign problem. We have a beautiful code, continuous time, but we cannot do much more than the attractive Hubbard model. What if you want to go to the repulsive case wave from half filling? The sign problem kills you immediately. But what one can do something called dynamical mean field theory, which is a very successful method for qualitatively describing the Hubbard model. And the basic idea is like in a standard mean field theory, let's say for a spin model, where we replace all spins but one by some path, by some effective field, and then we have a self-consistency condition that the net magnetization of the spin is the same as the path. In DMFT, one takes the same for the fermions that are hopping on a lattice. I pick out one lattice site. The rest gets replaced by a non-interacting path. And then I have a model which is just a quantum impurity model. There's this single site here, and the fermions hop from the site to the path and back. The path is non-interacting, and only that one site that I've picked out is the interacting. And I have to choose the path again in a self-consistent way. So what we do for that is we start from the lattice model. We use the Green's function of the lattice model to set up a path. We solve the path. We measure the Green's function of this quantum impurity model. From the Green's function, we extract the the self-energy, which is local here. And now we make the approximation that we say, okay, we use the same self-energy for the lattice model. And then for the lattice model with that same lattice, the self-energy, we calculate the path again, and we iterate this until it converges. So we replaced the lattice model by a single fermion site coupled to a free fermion path, and the approximation was that the self-energy is local and thus independent of the momentum. And that works pretty well for a Hubbard model. But the hard thing here is still, after I've mapped it to the quantum impurity model, I still have to solve that problem. Yes?
Is it clear that you save the physics that you really care about?
You save all of the local physics. So, and you solve all of the free fermion physics. So in the limit where the interaction is small, then it's basically the free fermion physics, and that you have exactly. In the other limit where the repulsion is strong, the important physics there is that of the Monte insulator, that things become insulating, and that's local physics. You just don't want to have two fermions on the site, and that you keep because you solve the local problem exactly. So those two limits of U being large at half filling, or U being very small, those two limits are kept, and in between you have to hope and pray.
Can you solve the two fermion problem in this way? For example, put two fermions in a lattice, interact with U interaction, attractive, repulsive, and so on, and this method will lead to an exact result or not?
For the two fermion problem,
On the lattice.
I think the two fermion problem on the lattice will be solved exactly.
But you see, because the problem I have is,
Because it's very dilute.
well, I understand.
And
But
the
see,
only
the problem I have is, see, because if I have attraction,
yes,
the two fermions will form a pair.
yes,
You see, and the other fermion, you see, if I look at this one, you see, I cannot think of the other one to be a bath for this one, because they'll be strongly correlated. You see, whatever this moves, the other one moves.
Moves.
In the rest, nothing happens. So I don't see how that solution emerges, you see, in the picture you just drawn.
For the two fermion problem, at a strong attraction U, the two will form an on-site pair.
Well, it could be on-site. it could
On-site.
be slightly
When
in
it
the radius.
when it's slightly larger, then it's qualitatively okay, but not quantitatively.
What are the limits?
This will work for weak interaction,
Weak attractive or weak repulsive?
weak
or
attractive,
whatever?
weak whatever.
Okay.
Because for weak
So it's
attraction,
perturbed
yeah.
method then?
So for
If it's weak, it's perturbed.
it works for weak attraction, yes, but it also works for very strong attractions. Because for very strong attractions, it will form a local pair. And that's
the bath then.
the path is then just that that pair can virtually hop by breaking and recombining.
One should also say the infinite dimension limit. This is exact.
Yes, it's also exact for infinite dimensions, which is some kind of mean field limit.
Is the self-consistency condition unique? Is there just one solution that you?
No, not always.
And then, because normally you have to look at the free energy or something to decide
Yes.
which of these. Do you have to do that here as well?
You have to do that here as well. For example, if we go into a Monte insulator on a cubic lattice, for example, which will have magnetic ordering, then as long as you're above the nail temperature, you will get the same solution for the up and down spin species When you go below, you will break that symmetry. And then you have to pick out which one has the lower free energy, or here it's easy because you just pick the best one from the physics. When you're close to the Mott transition, the Mott transition in this approximation is first order, and then you have to choose from the free energy which phase you're in. Now, I'm not saying that this is a good quantitative method. I'm saying actually it does not work in general. I'm just saying why people have used it. And then I will show you how to make it quantitatively accurate. So this is exact.
Can I ask
Yeah.
another question?
Yes. Yeah.
It's the following. You see, if this is exact in infinite dimension, is because the kinetic energy dominates at that point over the interaction energy? If I solve, for example, the Laplacian,
you have to rescale it in a certain way, because if you just keep the hopping constants, the hopping terms constant, and scale it up, then the
So that statement should be made more precise. For example, not as
you go.
as it sounds.
Yes, so it is exact on the beta lattice.
Okay.
That's the exact statement.
So what happens with the strength of the interaction? You scale it up. Or
You have to
scale it down?
you have to scale it up as you
Okay.
increase the number of neighbors. Yes. Why people have used it is because you can describe both the weakly acting limit and the Mott physics in one method. What we're going to do later to make it exact is we're going to look at bigger sizes of the impurity. And we use then 2 sites, 4, 60 sites, 100 sites coupled to the path around it. And that converges faster than if I just use the lattice model. So the expensive step here is to solve even the problem of a single site coupled to the bath, and that was typically done by the Hirsch-Phi solver, where one decouples the action using a standard Hubbard-Stratonovich transformation. One then integrates out the fermions and samples over the auxiliary fields, and there is no sign problem for the quantum impurity problem, no matter what the filling is or the fields are, because it's a single site problem. And that was the standard solver for 20 years. Now in the last 6 years, we others invented new methods based on continuous time. And the basic idea there is we don't discretize time first, but we split the Hamiltonian into two parts, perturbation and the part that we solve exactly, H1 and H2. We treat H1 exactly. We go into the interaction representation with regards to H1, and then we write down a perturbative expansion in H2, and that's what we sample. So this is a standard time-dependent perturbation, the expansion that we sample by by Monte Carlo methods. There are three methods that, yeah. Mm-hmm.
Why did they separate the exponential? Because H1 and H2 probably don't commute. So they should enter as a sum in the exponent.
H1 and H2 don't commute, but this is the time-dependent H. This is the H2 in the interaction representation.
Oh, I see.
Yeah. So we simply pulled out the global factor here.
Okay.
So this is then so
That's the perturbative expansion.
yes. So and so here's the time ordering, and so I propagate from tau 1 to tau 2 with H1, then I act with H2, then I propagate with H1 again. Yeah, just standard. And there are three different ways I can perturb in the interaction. That's what we now call the CT-INT method, the interaction, the expansion. That's due to Rubtsov. There is the CT-AUX method, the auxiliary field method, where we do a Hubbard which decoupling of the interaction in continuous time. And there's the hybridization expansion method, where we treat the Hubbard U exactly and we perturb in the hopping to the path.
Again, explain.
Yes. So the first one I want to show is the CT-AUX method, the auxiliary field one that was first invented for the Hubbard model by Rombu and for the quantum impurity problem by my student Gull. What we do here is we treat, so here we expand in the Hubbard U term, and the Hubbard U term we decouple using Hubbard Stratonov, which transfer deformation after the expansion, and then in kth order we get k Hubbard Stratonov fields, and after that we integrate out the fermions, and we end up with an effective action for these auxiliary fields. Now this is not a constant number of fields, but the number of fields change because I have a field term wherever I put like a Hubbard U in the expansion. And so now the weight depends on the fields and the times where I place them.
Will this, can you generalize this beyond Hubbard model, this transformation? Hubbard model seems to be trivial.
For Hubbard it's trivial. Beyond Hubbard models, you can do it. It was done for a Condor model. You have to think harder about other models.
So there is no solution.
You can do it for a negative.
Coulomb problem, for example?
If you restrict the Coulomb to the density part only, then it can be done. If you want the full Coulomb with the exchange, then this is not the method you want to use. So the updates are easy. I just insert extra spins at some times, or I take them out. And one more out. And I calculate the ratio of the weights. It's the same as we did here. Plus now we have to calculate calculate the ratios of the determinants, and that's like in a standard discrete time method.
What about the sign problem?
For the single site, in the case there is no sign problem here.
Single site. Where is the single site here?
If you have a single impurity site, which you have in your so one fermion or two fermion, there can be one up and one down, but coupled to a path, yes.
So
but
you're not really doing the full Hubbard model here.
No.
I'm mapping the Hubbard model to a self-consistent single site problem coupled to a path, and that single site problem, if you do it in a smart way, has no sign problem. Once you go to a cluster of sites, you get a sign problem back in the cluster size.
So you're solving the dynamical mean field.
Yes, exactly. Yes.
Okay, yeah, that's all right.
You can apply the same to the Hubbard model. If you apply the same method to the Hubbard model, then you get the sign problem immediately.
After the second order.
Yes.
Is there any kind of truncation in the degree of the power series expansion?
No, you don't have to truncate because the higher orders are suppressed exponentially since we are at finite temperatures. If you want to push it to the ground state, then it increases with beta. So this is exact up to the sampling error and the approximation we made in the DMFT approach.
Can I ask a general question? See, you make a case for the continuous problem,
Yes.
continuous time.
Mm-hmm.
On the other hand, if you work on a lattice, you have the highest energy data, which defines naturally the cutoff in
Yes.
energy, which defines naturally
Mm-hmm.
the discrete time step.
Yes.
So why go to this to make it continuous? So can you make
Yeah.
it clearer?
If I were
Because
in,
it's still
yes, no,
the problem
okay.
is discrete by definition in time.
Yes, so, but if I'm interested just in the critical point of some field theory, then I don't care at all. But here I have this physical lattice, and the lattice spacing is just given by the physics of my optical lattice or my material. And I want to know the exact properties of that specific microscopic Hamiltonian, where the physics has the spatial cutoff, but no temporal cutoff in the model.
Well, you have a maximum energy there, you see, don't go beyond.
I have a maximum energy, and if I make my time step small enough, then it's fine.
Yeah.
If I keep a finite time step, I get some Trotter error.
So how does
And that Trotter error,
compares here, you see, with the
Okay,
input
so
factor?
the typical thing is if I choose my finite time step as 1/10 of the spacing between my spins here, then it can still, for some quantities, give me qualitatively wrong results.
That I would agree.
So I need to choose my finite time steps about at least 10 times finer than the mean distance between my spins in the continuous time method.
And you
That
don't lose anything.
that seems to be small, but anyway.
And you don't lose anything.
Yeah.
You can do the whole thing in continuous time.
Okay, so
No, I understand it doesn't, you see, but I don't understand why the
Yeah.
point to do it.
okay, so
Not to use this irregular discrete time.
Equally simple
no,
for it.
no,
It's equally simple.
No.
Okay, I can use that.
Yeah.
no.
Do I have
There's
to make the effort to learn this?
there's a very good point. We've seen cases where you really have to make the finite time step 10 times smaller than the spacing between the spins.
So you are going to explain the physics beyond that? Why?
This is Trotter error, and I look at quantities and I want to know them to 5%, and then I need to make that small enough.
So I think, just to comment, I think if you don't need to do that, you don't have to do that. The
Yes.
whole method applies even without that.
Mhm.
That's all, I guess.
But also it depends how you approximate the total product, because it could be for some observable your error is of order of the times. And then you have
Yeah.
linear extrapolation to time step 0.
Yes.
So you take a very small time step,
Type.
it's still not good enough. You have to do the full linear extrapolation.
Yes.
Which we find in the color
So you need the time step that's at least 0.1 of the hopping t. If you don't do an extrapolation or negative time step of maybe 0.5, 0.3, 0.2 if
It's not
you.
only the hopping, it's the interaction.
Yes.
It depends which one dominates.
Yeah.
That depends actually on the time step.
Yes, what we've seen is that if one compares results with discrete time and without, we had one case where we looked at the double occupancy as the function of temperature. And if you do that in discrete time, it seems to have a peak around the nail temperature. If you do it in continuous time, there's no peak. And people claim this peak indicates the nail transition. If you do it in continuous time, that peak vanishes.
Cut-off energy. So, you see that?
The temperature here is about 0.3 times the hopping.
Okay, so that's too big. I mean, the time step.
Yes.
Yeah, clear.
So I wouldn't worry too much if this time step is about 10 times smaller, a safe factor of 10 in memory. But here, because I have to work with the determinants, the effort is cubic in the size of the matrix. So if I can keep the matrix 10 times smaller, I will be a factor of 1,000 faster. And that's a huge advantage that we have here. For the bosons and spins, it's 5 times faster, 10 times, I don't care much. Here, if I make the matrix a factor of 10 or 20 smaller, that's a big advantage. And that's the main reason why we go to continuous time. Now, the second idea is we can just expand in U and sample the vertices of the Hubbard interaction, that is the CT-INT method by Rubtsov. He has to introduce some factors here that he has to choose in a smart way so that there's no sign problem. He has to choose one of them to be maybe 0, the other be 1, or one of them be plus 1/2, the other minus 1/2.
Sign problem is small.
For the single side, there's no sign problem if you choose them correctly. If you choose them wrong, there's a sign problem. What we found then in the end is it actually makes sense to choose 2 different values and sample from them, and in that limit it becomes identical to the auxiliary field method.
It's like a fluctuating mean field.
Yeah. Yes. If we choose just one value here we expand, we get the times where we inserted the vertices. The updates are just I insert or I remove a vertex. This is not as stable as the other method, because I have to choose these alphas here differently for the upspins and the downspins, and then I break a symmetry. And then things tend to get stuck in some parts of the configuration space. So that method we don't use anymore. What we then use is, if you want to go beyond Hubbard, if you want to go to full Coulomb interaction, for example, or if the Hubbard U is very large, then we want to treat the Hubbard U exactly, and we want to perturb in the hopping. So now we treat the Hubbard U and the chemical potential and the bath term exactly, and we perturb in the hopping from the side to the bath and back. And then we integrate out the bath, and we again get a determinant from the path. How do the configurations look like now? We go to the eigenbases of the site, which are here just the occupation numbers. We might have when the upspin the subsite here is empty. Then the upspin hops in, it stays there a bit, and hops back to the path, and the downspin was gone, hopped in, jumped out, came back, and jumped out again. The weights come from the local Hubbard U here and here. It comes from the chemical potential mu, and it comes from the fermion lines of how these hop out to the path and back. If I sample the fermion lines, then I get a sign problem. If I sum them up into a determinant, then the sign problem is gone again. The updates here is just if you insert segments, remove segments, move segments around, and calculate the new weights. Yes. They all scale as beta cubed. Because the order k of the matrix scales as beta. So the method scale as beta cubed. Here we show the matrix size as a function of beta for Hirsch-Phi, for the CT-INT method or the CT-AUX method, and for the hybridization method for a large U. When U is larger than the hopping, then that's what you prefer. And the effort is cubic in the matrix size, and the matrix size here is typically about a factor of, okay, here's about 10, and there's about 100 here, 50, so it's easily a factor of 15 or 20 smaller, which makes those methods much faster.
So you picked some tau for Hirsch-Phi, presumably?
We picked the tau of 0.2. If you compare CT-INT or AUX against CT-Hype, then we see that when U is larger than about 1.5, you win with the hybridization method. So when I get U is large, then per turbine T, when U is small, per turbine U. That's pretty obvious. And here, that kink here, that is the mod transition where things change a bit. And we typically want to look around here for a U around 4 or larger. So for the single site problem, use the CT-Hype method there. But now we want to go to a 3D Hubbard model and want to do things exactly. And what exactly do we want to know? We want to know basically everything. We want to know the equation of state, the density, the energy, the entropy, the free energy. We want to know the density correlations, the spin correlation function, and so on. What do... Yeah? This is what we...
No, make the list of what you don't want to know. That will be shorter.
We want to know everything that the experimentalists want to measure. So what? Yes. We don't want to know anything beyond 4-point correlation functions. We want to know the 2.1 and the 4.1. It's short, yes. We want to know it but we mostly want to know it equal time correlation functions. Although later we want to know also dynamic. But what do we really need to know for the experiments? They want to know how far do they have to cool to see nail order. So what is the nail temperature, or rather what is the entropy at which they reach nail order, because they work not at the constant temperature but at constant entropy. So what is the entropy at the nail transition? And going there, they want to compare what they measure to quantum Monte Carlo simulations. They can measure the densities, they can measure spin correlation functions. So we want to know some data for what they can measure. The idea is we use our data to check the experiments, then they drive their experiment into a region where we cannot just simulate, and then we trust them afterwards. And now, as we discussed, the MFT is not exact, because basically what it amounts to is that I assume the self-energy to be local, so the self-energy to be independent of the momentum, which is typically not the case in an interacting system. And so what one can do is now I can say, let me not make it local in k-space, but let me make it piecewise constant in some patches of the Brillouin zone. And I approximate it by sum over piecewise constant functions in some local patch. And then that then gives me an impurity problem where I don't solve for a single site but for a cluster of sites. When I use 100 sites, I get 100 patches in k-space where it's piecewise constant. And that way I can make it exact, because as I let the cluster size go to infinity, the method becomes exact, and it converges here faster than the lattice simulation. So what can I do to go to larger systems? If I use the CT-AUX, then the scaling is cubic. A sign problem sets in, but it's not too bad on a small cluster. We have done that for up to 100 sites, but it's restricted to Hubbard-like models. If I use the CT-Hype method, there we have to solve the impurity problem exactly, because we have to work in the eigenbasis of the impurity, so that becomes exponential in the cluster size. There we are not restricted regarding the interactions. We can do Coulomb, but we can't really do more than 5 to maybe 7 orbitals. So for the Hubbard model, we go with CT-AUX. And it's really crucial that we don't pick a fixed cluster size, but that we extrapolate in the cluster size. And here we showed that for the energy, and things extrapolate nicely in the cluster size. Here I show the self-energy. Yeah. That's analytically known if you start from this is known in some limits, and it seems to work well. Yeah, okay.
Don't claim that I know the answer.
No.
Yes, sir.
If we look at the self-energy, which we show here for the 3D Hubbard model at the nail transition, then in the single side method, we think is constant. That's the green line here. When you go to a cluster of 18 sides, it's the red line. Things get better. That's what people did before. With the continuous time methods, the matrices are about the factor of 10 smaller, which we can use to make the cluster a factor of 10 bigger and still do the calculations. So we went to 80 sides and 100 sides, and then things slowly start to converge. What that shows is that at the nail temperature, I would never trust the single side calculation. Let us compare the methods. Here, that's at half filling. I'm showing the entropy per particle as the function of the temperature, and down to the temperature of the hopping. The DMF T method agrees with the high temperature series and with all other methods. DMFT for the nail transition that it gets predicts an entropy of log 2 because it's a mean field method. The true entropy at the nail transition is around 0.4 something. And when we go down here, then the lattice calculation agrees with the cluster DMFT method, which is the extrapolated the DCA here, except that the lattice calculation has the much bigger error bars. So it works. If we look at the depends on the cluster size, if the temperature is about 1, then the self-energy is roughly constant still, and when we go to 200 sites, then things have converged. Then you go to lower temperatures like 0.5 of the hopping, then things still look pretty good. Converge when you go to lower ones even, then the 84 and the 100 side cluster no longer agrees. So below that, I would not trust those methods for the quantitative results. And that answers the question about how well can you trust DMFT. We find that we can trust it completely down to the temperature of the hopping. When you go to much lower filling, we can trust it down to lower temperatures. You can basically trust it as long as all the physics you want to know is local or that of free electrons. You have to go to clusters to include the correlations. And once you get long-range order, then things become tricky. So what have we used that for? We calculated not all quantities, but just the energy, entropy, density, the free energy, some charge correlation, and the nearest neighbor spin correlations. And that's useful because, of course, we said here, if you can measure in the cold atoms what the nearest neighbor spin correlation is, then we can tell you at that value the temperature is 0.5 of the hopping. So that way they can measure the temperature by comparing to the QMC data. What you also looked at then is what is the entropy they have to cool the system to get the nail state, because that's the crucial question. They're now typically at an entropy of about 1.2 per particle. The nail temperature in the homogeneous system is about 0.41, the entropy there. So they have to reduce the entropy by about a factor of 3, which means lots of cooling. But the system is not homogeneous, but the system is in a trap. In the trap, the central region might be in a mod state, might be nail ordered, but outside there's a huge region of metallic shell that can pick up enough entropy to make it nail ordered in the center. And so here we now plot the entropy in a trap as the function of the distance from the center. So that's the entropy per lattice site that I show here. And it goes down and down and down, and as you go to low temperatures, you have lots of entropy in the metallic shell on the outside, and in the center it can be smaller, so that when you go to the nail temperature, then it's enough to have about 0.65 kb of entropy per particle, and still in the center it will be the 0.4 per particle, and you get the long-range nail order. So we only have to cool further by a factor of 2 instead of 3. That's the good news. The bad news is they have not achieved that yet. What they have got is they looked now in the group of Esslinger. They measured now finally the nearest neighbor the spin correlation function. The way they do that is they take the two lattice sites, they merge two sites into one, and then they locally form a molecule from the two atoms which are there. If the two atoms are in a singlet state, then it works. It forms a molecule. When the two atoms are in a triplet state, it will not form one. And so by counting the number of molecules they form, they measure how many nearest neighbor singlet pairs they have in the model. And they didn't find much for the isotropic cubic lattice. So then they turned on and made the hopping in one direction much stronger. So they went to the limit of the weakly coupled chains and looked what happens there. And they did find that as they make it more and more anisotropic, the number of the singlet pairs goes up and it starts to order magnetically. So they see it goes up quite a bit, and it goes up to about a quarter of the maximum value one can get if one has this perfect singlet. So now the question is, does it mean they get nail order finally? Because they have this strong nearest neighbor correlation now. And that was their hope. But they had no way of telling. And so in comes the quantum Monte Carlo. And here we plot the nearest neighbor the spin correlator that they measured as a function of the entropy they have in their cloud. And at high entropy, it decreased pretty well. with the blue line, which is the simulation for the anisotropic system. The green line is the same entropy for the isotropic one. So by going to the anisotropic system, it does order more at the same entropy. At lower temperatures, it goes down again. And the reason we think is that there they just have not equilibrated yet in the time they run the experiment. So those numbers I wouldn't trust because, again, they don't agree with the quantum Monte Carlo. They are probably too hotter than they think they are, or it's not equilibrated. I think it's the latter, probably. Now, we also see that as we take the trap and we look at what is the temperature at a given total entropy, if we make the hoppings anisotropic, the temperature goes down a little bit, but not much, a few percent. So have they reached nail order or not? And the answer is, unfortunately, we don't think they have reached it, because if you go to such an anisotropic lattice here with the ratio of 8, the nail temperature drops by about a factor of 4. So we are farther away from the nail temperature, actually. And if you look at the spin correlation function, that decays rapidly exponentially at those temperatures. The nearest neighbor one is large still. The next nearest neighbor one is smaller by a factor of about 100. So it's really only local ordering. Why do they then see so much more signal for the anisotropic problem than the isotropic one? That's simply because in 1D or in quasi-1D, they form singlets only with 2 neighbors. In 3D, they have to form singlets with 6 neighbors. And so when you look at one singlet, correlated that is reduced. It's more mean field-like than in 1D. In 1D, you can build up more local correlations because there are more fluctuations possible than in 3D. So that's basically what they see here. As one makes it more 1D-like, you have more fluctuations, so you see more local correlations, but unfortunately, the long-range correlations are just tiny. So to summarize with the continuous time methods, we've made a big improvement for the quantum impurity solvers for the MFT. The new codes are faster, more flexible, and also more accurate. We can go to the temperatures for the Hubbard model that are 3 times lower than what they can reach in the experiments, which means that they cannot teach us much there yet. For materials, it's harder because the models are more complex. We have Coulomb interactions, we have phonons in it, we have frequency-dependent effective models, and that is work in progress on the solvers. Thank you. More questions?
So DMST is also used within LDA to
Yes.
look at chemical materials.
Yes.
From a chemical Hamiltonian point of view. You talked exclusively about more the Hubbard approach, for the Hubbard model. Do you see, what is your opinion for the role that the MFT, for a cluster DMFT specifically, would have in more material science?
Okay, so there are a few problems there. And okay, so first of all, it does capture the Mott transition qualitatively, which is a big first step. About quantitative agreement is you have two problems. The first problem is, like we see here for Hubbard, you want to go beyond a single site.
Right.
But the second problem is you also want to go beyond a single orbital locally, because it's not just the Hubbard model, but you have full Coulomb. So the problem of going beyond a single orbital has been solved with the CT-Hype. You can do up to 5 or 7 orbitals, so you can do actinides, that's no problem, as long as there's only a single atom in the unit cell. Going beyond that is hard, because for the full Coulomb, the CT-AUX doesn't really work. And the other scales exponentially. So we will be stuck with the single site method. What is the problem for the single site method? The main problem is not the DMFT approximation. The main problem that I see is the double counting problem. We add in the Hubbard U or the Coulomb, which we have to subtract from the DFT. And depending on how you do that, the results differ a lot. So that's the main problem that has to be solved there. And
So you don't see a way of expanding the cluster, at least in a straightforward? Is it a matter of, well, I guess it's a matter of computation.
No, we can probably do a 2-site cluster if we have only about 3 orbitals per
So it's a matter of how many orbitals you can
per site. Yes, we can do about 7 orbitals. I see a way of expanding it further to about 100 if you give me a quantum computer. That combined with LDA, and this will do it. The quantum computer alone will not help you too much.
Is a D-wave quantum computer good enough?
A D-wave machine cannot solve that. No.
So at this point, what do the experimentalists say in terms of the prospect of improving the experiment to become better than TO?
The problem with cooling further is that they have heating mechanisms from the lattice laser itself, the photon of the laser, and from the background the gas atoms that just hit out the particle. Imagine you cool this Fermi gas down to a very low temperature, and then you kick out one particle from deep in the Fermi sea. You're basically hot again. Or the lattice laser photons, they can localize a particle, and that's the same problem. It's localized now, it's hot. So they've tried that for many years, and the big success now after 3 years was seeing local correlations, but I don't see them getting colder. Yet. So I think their big advantage is they can do dynamics of the system, which we can't really do by the quantum Monte Carlo. So they should rather focus on transport properties, dynamical properties. That's the big advantage they have. I don't think they will ever to compete on ground state properties of any quantum model.
But I know in general they claim that the scaling, they can go to large system.
They can go to 100,000. Fermions at a temperature that's about the hopping, where the correlation length is about 1 lattice spacing. I don't care about the big system then. But transport at those temperatures is non-trivial. Yes.
More questions or comments? No, thank you.
Yeah.
And again, we recombine